Okay, time to start. Let's continue where we left off last time. Do you remember where that was?
We were running stuff and stuff. Yes, we were running a one-way, non-perimetric.
Ooh, good job. A one-way, non-parametric. Hey, it's working today. Parametric test. You could also put the word ANOVA there, and that's section 15.3. If you make it ANOVA. So far, we've done what is analogous to a two-sample t-test, and that's the Wilcoxon rank sum test, right? So, two-sample t-test is the parametric test. The non-parametric test is the Wilcoxon rank sum, RS for rank sum, because I was running out of space, right? So I got a little bit to finish up with that today, and then we're going to go to section 15.2, which is the paired t-test analog in non-parametric. So on this side is the parametric test, and on this side is the non-parametric test. And this is also due to Wilcoxon, but it's now, instead of the rank sum test, it's the signed rank test.
And what is the paired t-test in our calculator?
Good question. What is a paired t-test? What does the word paired make you think of? Okay, two things put together. So it's a two-sample means problem, but those two samples are paired. They can be put together. All right? Usually, that's a pre-test, post-test kind of scenario. Right? So I give somebody, I recruit somebody to be in my clinical trial, and I take their symptom scores, say it's allergy, during baseline. Then I put them on treatment, and I follow them for 6 weeks or whatever, and then I test their symptoms again. Now I got two observations from the same subject, right? Those two observations are paired, so that's called paired. And it isn't what their mean was at baseline compared to what the mean is at post-treatment that really matters. What matters is how much did they change. So it's the difference. So if you remember the paired t-test, you take the differences between sample 1 and sample 2 within each pair. And then it reduces to a one-sample problem, one sample of differences. So to answer your question, Taylor, in our calculator, this is t-interval or t-test on the differences. So it reduces to a one-sample problem. And the Wilcoxon signed rank test does the same sort of thing. It worries about the differences between the two samples. All right? But we'll get to that today. And then the next section, which we won't get to today, is the one-way ANOVA. Which, what we've done so far, the one-way ANOVA, where we had a factor at so many levels or whatever, how is that a parametric test? We talked about parametric. The t-test is a parametric test. Why do we call it that? Okay, it makes an assumption about the distribution. And that assumption is? You have normally distributed data. What about one-way ANOVA? Is that parametric? Yes. And what's the parametric assumption there? The distribution assumption? Same thing. Normal, and the samples are independent. It's just now you got more than two of them, so we have to step up to one-way ANOVA. But it's really a one-way ANOVA on a factor that only has two levels will give you exactly the same p-value that a two-sample t-test would give you. It's an F test instead of a T test, but the p-value will be exactly the same. So the non-parametric analog to one-way ANOVA, so more than 2 levels, is the Kruskal-Wallis test. But it's really just the Wilcoxon rank sum test applied to more than 2 groups. Right? So now instead of picking one of the 2 groups and summing the ranks of that group, you sum the ranks of all the groups, and then you do a little bit different test statistic on that. But like I said, we won't get to that today, but it's good to have this all in one place in your notes so you can keep it straight. Because when you read the next test, when you read a question, it's not going to say, here comes a Wilcoxon rank sum test. It's just going to give you a scenario with some data and say, do the appropriate non-parametric test. Okay? So you have to be able to decide, well, which one do I use in that scenario? Okay? So, let's remember about the rank sum test. So I'm dispensing with the word the name Wilcoxon, but the rank sum test, remember we talked about, well, remind me, we've got 2 groups. So what's just in words, what's the step-by-step method of performing this test? Okay, you ignore what group they're in, and you rank them smallest to largest. Right? Then circle all of those ranks that came from one of the groups, doesn't matter which one, and then sum the ranks that got circled. Right? And then you can form a approximation to the test by forming a test statistic out of that rank sum, converting it to standard normal and using your normal CDF function or whatever to do a p-value. Then also remember that the normal CDF, we used a continuity correction in there. And SAS is going to do all this automatically. Right? The one thing that we didn't talk about before is, what do you do if there's ties? Right? So let's say I'm going to make up some data here, but this is group A, and let's say we had values of 98, 86, 75, and 80. And then in group B, we had 80, 86, 78, 80, and 100. And remember, our sample sizes don't have to be the same. The example we went through last time, we did have equal sample sizes, but they don't have to be. There's nothing magic about that. All right, so let's rank them. So putting them in order, the smallest value is 80, and there's 3 of them. So
Sorry, 75.
Oh, yeah. I shouldn't listen to Taylor. 75, 78, and then 3 80s. And then 2 86s. And then a 98 and a 100. Did I get them all? So there's 4 plus 5 is 9. Yeah, I got 9 numbers there. Right? So now the question is, what do we do with these ties? Well, what you do with the ties is what common sense, you'd probably come to that. If you were making this up, if you were Wilcoxon, you'd have to think, well, what am I going to do if there's ties? What would the natural thing be to do?
Rank them the same.
Okay, give them all equal ranks, and what would that equal rank be? Okay, so this is 1, this is 2. If they weren't tied, this would be 3, 4, 5. So give them all 3s. What did you say, Laura? Give them all 4. That's right. And where'd you get 4? It's the average of the ranks they would get if they weren't the same. So these would be 1 or 3. Use my finger to erase. This would be 3, 4, and 5. The average of those is 4, so we give them all 4. Now, what would the 86 get? 6.5. Very good. Because if there were no ties, this would be 6, 7. So then I give them the average of 6 and 7, so they get 6.5, 6.5. And then 8 and 9. Now if I go back and circle the ones that came from group A, I would get the 98, I would get the 86, and now it doesn't matter, well, which one of those came from A? It doesn't matter, they got the same rank. Right? So circle one of them, but not both of them. And then one of the 80s and one of the 75. I didn't get my 8 circled, but so then the rank sum for group A is 1 plus 4, which is 5, plus 6.5, which is 11.5, plus 8, which is 19.5. So W for group A is, I already forgot what I said, 19.5? 19.5. Okay? Yeah.
So you said it doesn't matter which group you pick, right? Even though they're different sample sizes.
Right. It is okay because the way the test statistic is formed takes that into account. So where it gets affected is the expected value of W is weighted by sample size. So if I'm doing WA, then the expected value is going to be less than it would be for if I was summing B, because B's got one more rank to add in. So, yeah.
Why would you do a weighted mean when you break up the rank for 380s?
And weighted by sample size?
Well, there's 180 in group A, 280s in group B.
You know, that has never occurred to me. But that's a good thought. It's probably been looked at, and it probably ends up not making a difference. I don't know. Or perhaps, I don't know if the video could hear what he said, so I'm going to repeat it. But he said, how come you don't do a weighted mean of the ranks, since 2 of the 3 ties came from group B and only 1 of them came from group A? Why would you put them all the same instead of doing like a weighted mean of some kind? And, you know, this is where you do research in statistical theory. Right? People always, when people ask me what I do, well, I'm a professor, I teach statistics, and oh, so you have to do publications. Yeah, well, how do you do publications in a math subject or in statistics? You know, they understand about measuring leaves or you know the sciences, but they don't get how math is a science. Well, that's what it is. Okay, what would the properties be if instead I did a weighted mean? What would my expected value be? What would my test statistic? How would I derive it? What would the distribution of that be? Finding out, doing the theory behind the scenes to figure that out, and maybe you get a test that has better performance.
Building better tools.
Yeah, building better tools. So, you know, I don't know. That's a good question, but we just don't, because Wilcoxon didn't say to. But that's the kind of thing that is open questions for doing PhD dissertations on, things like that. Okay, so that's the only thing we really had left to do with the rank sum test, other than finish doing it in SAS. So we see how. Actually, we might have went ahead and we finished this problem in SAS, but let's go back and look at the results and make sure we got through all of the interpretation of that.
Yeah, we ran out of time, if I remember correctly.
So let me come to here, and I'm going to remember, but you'll have to remember to tell me which buttons I have to do to undo things. And this always expands so much when I do that I can't There we go. Then I want to go here. Oh, I got to do that. Then, okay. So now, this is, I saved the project that we were doing before. Let's see, I want to get rid of this. And so I have the hotel rooms and imported the data, ran the non-parametric ANOVA, and then got the output. So I'll double click on that so we can look at the output that we got back. So I remember we were doing things by hand and we were matching the numbers in here. You remember that? So you want to make sure you understand how to do that, because on the test I may give you SAS output like this and say, here's the data. The data was run in SAS. Here's the output, but I'll blank out that negative 1.25 and say compute the value that goes in there. Something like that. All right? So any questions about that? That's the only one that our book teaches, is this normal approximation, and that is with continuity correction. There's also the exact test, which doesn't do this approximation. It actually uses the exact distribution, which is complicated, uses a lot of computing power and all that. There's a slightly different T approximation that somebody else published that said, hey, this actually has better performance or whatever, or at least different in certain data sets. But the p-values are awful close. So this p-value has a two-sided p-value of 0.21. This one is 0.24. They're going to make the same conclusion. All right. Any questions about the SAS output? So what is the conclusion?
Reject the null. And then you said we have to go over the null. But that is what you said last time. We haven't gone over what the actual null is and alternative is. But
Okay.
we reject the null.
Do we reject the null?
Fail to reject.
Fail to reject the null. Right? So we fail to reject the null. So what would the null be?
That's what you were saying.
In words. Okay, there's not a difference. And remember what we're measuring here? It's the top-ranked spas versus the lower-ranked spas. Is there a difference in the number of hotel rooms in those spas? So maybe it's that, the better spas don't have as many rooms. So they have bigger rooms, or who knows. Or maybe it's that they have more rooms. It's hard to say. But what is the conclusion here? Yeah, well, you can't say there's no difference. There's
significant difference between
right.
the high-ranked spas compared to
Okay, good. There's not a statistically significant difference in the number of rooms. Or you can say there's not enough evidence to say there is a difference. There might be a difference, but we couldn't detect it with 5 in each group. All right. So now, let me finish that discussion about exactly what is the null hypothesis. Okay, so I need to do that. Then,
not enough evidence that there is a difference.
how do I got to get rid of this bar so I can get down to, or maybe I can, nope, that didn't work. Anybody know how to remove this bar or to move it so I can?
You just click on the third button from the left.
Yeah, if you don't want to be able.
There we go. Yeah, I
There's not
don't.
enough evidence that there is a difference, right?
Right, there's not enough evidence that there is a difference. Right, so now I need my page browser back. So view, browser, and so we'll go to the next one. What is exactly the null hypothesis? In words, we said there's no difference between the groups, or the alternative is there is a difference, right? There's a common misperception out there, and I actually just hit this with a consulting client about 2 weeks ago. she knew she had small sample sizes. And she was pretty sure that her data would not be normally distributed. So she knew she had to use or should use non-parametric tests. And she said, she wrote it up in her results that the null hypothesis was that the median for group A, actually let me just put a subscript. So median sub A equal median sub B. And that's an equal sign. Okay? That is true. That is the null hypothesis if you're willing to make one additional assumption. So
is that correct for us?
I don't know. Let's talk about that additional assumption. We say it's a non-parametric test. There are no distributional assumptions. But this is true if we can assume the two population distributions. Let's say it that way. The two population distributions have the same shape. We don't have to assume they're normal. They can be horribly skewed, but they both have to be skewed in the same way. All right? Have the same shape. So, if we can make that assumption, and that's usually acceptable to researchers to say, well, I don't know that the data will be normally distributed, but if one group is skewed, the other one would have the same skewness. You know, it makes sense that they would be the same. What about the hotel rooms? If the number of rooms among top-ranked spas, think of a histogram of the number of rooms in top-ranked spas.
I don't think it. My inclination would say that the less rooms, probably the higher rank, or at least I'd expect a lower amount of rooms in the higher end spas than for the lower end spas because they need more people to keep it running.
Okay. I don't know if you could hear that, but he said he expects that the higher ranked spas would tend to have less rooms and the lower end spas would tend to have more rooms. But what about the shape of those distributions? So think of, okay, the higher end spas have less rooms, but it might be that on a histogram they have some distribution, and this is maybe 50 rooms. Some of them, there's a few, you know, so it's a skewed distribution. Some of them have a lot of rooms, but most of them keep it pretty small. Whereas the other group, look at me using different colors. The other group is shifted so that its median is out here at 100, but they have the same shape. If you can assume they have the same shape, then you can say, yeah, you're testing a difference in medians. Right? If you can't say the same, that they have the same shape, if not the same shape, then the null is, in words, the groups have the same distribution versus they have a different distribution. So it becomes a much broader statement. The same distribution, alternative, I'll write this in an abbreviated way, different distributions.
doesn't that confuse though, like the number of, like the question about the number of rooms?
Yeah. If you're not able to say that, yeah, I think they would have the same shape, then you're just saying, well, the distributions are different. There is a difference in the distribution of number of rooms. Maybe they have the same center of that distribution, but the distribution is different somehow. It's not as strong a claim as saying the medians are different. The median number of rooms in top ranked is lower than the median number of rooms in the lower ranked.
So how would you make that jump? Because like when I'm sitting here thinking about the rooms, like as a business, if you're higher rated, you could probably charge more rates. Therefore, you don't need to have as many rooms. If you're lower rated, you probably need to charge lower rates to, again, still close to profit. So, I mean, how do you make that jump in our output?
In our output, you really can't. If you don't have some prior information, or at least some, in this case, the word biology doesn't make sense, but I always think some biological reason of why you think, yeah, those distributions would have the same shape, then there's no way to get from the data to test that. Because you can't draw a histogram from 5 rooms, right, and get any real sense of what the shape of that distribution is. But if you think about it, if you have, same picture I drew a minute ago, you got one group that's really skewed, its median is going to be just a little bit to the right of the peak, and you have another one that is nice and symmetric. My eraser's too thick. Nice and symmetric, that has the same median, but very different distribution. All you're saying is, nope, they're not the same distribution. Because you're more likely to get outliers from one of those two groups than from the other group, right? So you might come up with a statistically significant difference, even though they have the same median, right? So all you can say is, well, the distributions are different. In practical sense, I'm not sure it's that important to the researcher or to the hotel owners, right? They say, well, they have different distributions, so one of them tends to be more skewed, so they have higher number, they're more likely to have higher number of rooms because of those outliers. Then you say, you know, if that happened to be in the higher ranked group, then you say, well, so I maybe need more rooms. I need to be in that tail of the distribution. But it's kind of it's a subtle point that most non-statistics people don't even realize is there lurking behind the scenes, and they just assume, and I remember hearing this in graduate school, that the t-test is a means-based test, the Wilcoxon is a medians-based test, which, you know, I like that to say it that way, because what do you do for the Wilcoxon test? You rank things, you order them, right? And what do you do when you compute a median? You order them and you pick the middle number, right? So the median is an order statistic. It's a rank. You know, this one ranks 50th out of 100. And so it is sort of a medians-based test, but it's only truly testing for a difference in medians if you're willing to say the distributions have the same shape. Usually that is not very testable. But
so would you even go into Wilcoxon if you couldn't prove that they had the same shape?
yeah, you'd still use it because there's nothing else to use. Right? You'd still use it, but you just have to be careful on how you state your conclusion. You say, yeah, there's a difference between these groups, but not that the median is different.
So you just have to reference like a different study with a larger sample size looking at the distribution of groups.
Yeah, if you have a larger sample size, things get better quick. So you can do so much more with it.
Is kind of the 30 still kind of a nice number for that out of curiosity?
Yeah, the question is n equal 30. Does that give you a sample size big enough to make a conclusion. And what do you know about n equal 30 and the central limit theorem? If you have at least 30 in your sample, then the sampling distribution of x bar will be approximately normal, whether or not you have normal based. So then the t-test becomes valid. Right? Now I can't remember if this was we discussed during class or if it was after class, but Taylor asked me, I remember you asking me, so if the non-parametric test is always valid and the t-test is only valid sometimes, why would you ever use the t-test? Why don't you always use the Wilcoxon test? Did we talk about that in class? Nope? Okay, good. So answer that question. Taylor?
Because you said the t-test gives you more power.
That's right. So if the assumptions for the t-test are met, then you want to use the t-test. It's a more powerful test than the Wilcoxon test. Oh God, there's a word, power. Power is a word that you learn in MA343, the definition of it, but you don't learn how to compute it. And I'm not going to teach you how to compute it in this class either, but do you remember what power means? What does it mean to say the test is more powerful? What do you mean by more weight? Sort of, that's true, but...
You're going to have more credibility if you go to someone with the t-test than you do with the Wilcoxon.
No, not necessarily. The Wilcoxon is perfectly valid, so it's got all the credibility it needs.
You're going to be able to test different, or you're going to be able to identify more fluctuations easier with more power that you have.
Right. That's one way to say it. Let me go back to here, and so you remember what alpha is, right? In a statistical test, the significance level. So alpha is significance level, and it's the probability of a type something error. It's either 1 or 2. It's a type 1, right? Type 1 error is when you reject the null, but the null is actually true. Right? So there's really no difference, but your sample just, by random chance, made it look like there's a difference. Right? That's called a type 1 error. So alpha is the probability of making a type 1 error. So beta is the probability of making a type 2 error. Let me use the eraser. I forgot. This is a conditional probability, so I should say what the condition is. Both of these are conditional. The type 1 error, what does that imply? If it's a type 1 error, that implies the null is true. So I'm going to put 8, 0, true as condition. If the null is true, what's the probability you make a type 1 error? Now, beta is what we call the probability of a type 2 error given, what's the only way to make a type 2 error? If the null is false. So null is false, but this is a little bit of a problem. This is why we don't teach you how to compute this. This is readily computable. I don't know if that's a word. But this one, and you actually just pick that. You just say, I'm going to use alpha equal 0.05. So there's no issue about computing it. But beta depends on, well, how false is it? So if you say the null is false, that means the alternative is true. But the alternative is always something like this. Mu greater than 0. Well, I got to know what mu is before I can compute this probability. So greater than 0 doesn't help me. I have to say, well, the null is false, and so for a particular value, you have to set mu equal some value, right? So C for a constant. So you have to say, well, if the mean is greater than 0, and if the mean is 5, then you can compute this probability. It's a fairly easy cut. computation then. But this probability depends on how false the null is. You know, how far the truth, how far away from the null is that, right? And so this, remember, a type 2 error is you're failing to reject the null. You should, right? So your study wasn't powerful enough. So 1 minus beta, what, 1 minus a probability? If I say the probability that I roll a 1 or a 2 on a 6-sided die is 2/6, then 1 minus 2/6 is the probability of everything else that I don't roll a 2. So it's the probability of the complement. So what's the complement of making a type 2 error? Not making a type 2 error. So it's the probability of statistical significance given alternative value C, right? So null is false and the alternative is true with some value C. So you tell me what C is. So this is what this is called power. 1 minus beta is the power. So the power is the probability that you get statistical significance if the null or if the alternative has some set value. So we typically, when we design studies, we do what's called a power calculation. Same thing as a sample size calculation. So that's one of my roles as a statistical consultant is people will come and say, hey, well, we're going to do this trial. We need to know how many patients we need in the trial. So they give me information. So I have to have a value for the alternative. Say, so if I'm doing a drug study, I'll say, okay, so the null would say there's no difference between the two drugs, placebo and your drug, right? How much of a difference do you want to be able to detect? So let's say I'm doing a blood pressure medicine. If you want to detect a difference of 2 in, I can never remember, systolic and diastolic blood pressure, which is on the top, which is on the bottom. It's like a normal blood pressure is like 120/80, right? So the top number, 120. High blood pressure would be somebody that's above 140. So let's say I can move their 140 down to 138. Is that clinically meaningful? Probably not. So that's what we use here. We say, okay, what would be clinically meaningful? How big a difference do you want to make sure you detect? If I can move it 10 points, maybe that's getting somewhere.
Systolic over diastolic.
So systolic is on top. So systolic of 140. If I can move it by 10 points, so then I have a value for this C that I can plug in. I can do a power calculation, right? This was a long way around to explain what we mean by the t-test is more powerful. It's less likely to make a type 2 error. If the assumptions are met, then it's more, let me just say it this way, it'll have a smaller p-value. For the same data set, the t-test will have a smaller p-value, usually, than the Wilcoxon-Rank sum test.
It's finer grain.
Yeah. So it's more likely you'll have a better chance of declaring that there is a statistically significant difference.
So, but the more assumptions you have, that should always be the case.
That's right. Because the more assumptions that you have, they take away a lot of the noise. If you can say, well, these things are going to be normally distributed, then that takes away from the fact that it's symmetric distribution and p-values are computed, so. Make sense?
But that's not like when you figure out the sample size needed for a p-value, that's not the same thing as when you're calculating power.
No. You actually don't compute sample size to give you a certain p-value. You compute sample size to give you a certain power, a certain probability of success. So it's getting a p-value less than 0.05 in your study. So power is usually set high at like 80% or 90%, so that if the drug does what we think it does, then I got a 90% chance that my trial will be successful, meaning we'll get a significant p-value. Declare the drug is better than placebo. Okay? So that pretty well wraps up the Wilcoxon rank sum test. Let me see if there was anything else here. Yeah, there's other. When you run this in SAS Enterprise Guide, it does lots of other tests too. The Kolmogorov-Smirnov test, things like that. That sounds like a vodka, doesn't it? Kolmogorov-Smirnov test. Those are just different tests that all test whether there's a difference in groups. They're all non-parametric. It's just different than the Wilcoxon one. So you won't be responsible for those. But if you're programming in SAS, you can use options to not get those tests. But when you're using SAS Enterprise, it just by default gives you all of them. So you can ignore the ones you don't need. Okay, so now let's go back and let's see, I got to use my mouse to get back, I guess. Let's go back and talk about the next section, which is the Wilcoxon signed rank test. So I'm gonna ignore or suppress the word Wilcoxon. So a signed rank test. Remember, this was for paired data. Right, paired data. So the signed rank test is analogous to the paired t-test, and the paired t-test, thank you, takes the differences within each pair and makes one sample of differences. So how am I going to do this rank test if I only have one sample? Well, it works like this. You take the difference within each pair, if the null is true, what do you expect those differences to be? You'd expect no difference. You'd expect them to be 0. Except you know there's some random variability, so they're not all going to be 0. So what would be true about positives and negatives? They should be pretty well equally distributed at around 0, right? You should get about the same number of positive values and the same number of negative values, right? That's where the word signed comes in, the sign of the difference, right? So basically it's like the rank sum test, except now your grouping variable is the sign on it. You've got positives and you've got negatives, right? So add the ranks from the positives, and there's your rank sum, right? So take the difference within each pair. Then order the, so let me put numbers here. So step 1, step 2, order the absolute values. So order the differences by absolute value. In other words, ignore the sign. So if you get a -1 and you get a +1, they both have the same absolute value, right? So order the differences by their absolute value. And then you're going to rank them. Rank the absolute values. And again, just like the other test, for ties, use the average. Yeah, you know me better than that. And then the next step, circle. Just like we circled the ones from group A, now we're going to circle the ones from group positive. So circle the positive ones. You could also circle the negative ones, doesn't matter, but the book does it from the perspective of the positives. It's arbitrary, and then sum the ranks. Okay, and we'll call that test statistic W plus. So W plus is the rank sum of the positives. So, just like we did before, once we get a test statistic, or this is actually, I guess, not fully the test statistic yet. It's what Wilcoxon called the test statistic, but we're going to do the normal approximation thing again. So we've got to convert that into a Z test statistic. So in order to do that, what do I need to compute? Or the mean of those values and the standard error of those values. So what are all the possible W pluses you could get? What's the mean of all of them? And then what's the variability associated with those, right? So the mean of all of the W pluses, it's going to look similar to the rank sum thing, but now you have your sample sizes number of differences. There's not an N1 and an N2. Right? And instead of capital N being the sum of those two things, you just have little n times little n plus 1 divided by 4. Do you remember what the other one was? It was little n sub 1 times capital N plus 1 divided by 2 instead of by 4. Why is it over 4? Well, it's because the little n sub 1 was essentially capital N over 2, right? So now it's got the extra over 2 in there, so it becomes a 4 on the bottom, right? And then the variability, sigma sub W plus, is the square root. This will also look similar, but again, the bottom will be doubled from what you saw before. 2n plus 1 over, instead of 12, it's, and I wrote a 1, it's 24. Does that look like a 2?
Yes.
It kind of looks like an R. But. So 2n plus 1. Okay? And then I'm out of time, but from there, once you have those things, you're going to take your test statistic is going to be W plus minus the mean divided by sigma W plus. You get a test statistic out of that, which you can compute a...
And you still get closer to the 0, whichever way.
Right. To do your continuity correction, it's closer to 0 now. Now, the one thing that I still have 5 seconds that I can say is you exclude zeros. Right? So we have to decide if they're positive or negative. Well, and what do I do with something that's 0? If there's a pair that had exactly the same value pre and the same value post, that's a 0. So you just exclude the zeros.
Do you still add or minus? Is it still 0.5?
Mm-hmm.
Okay.
Yeah. It's still 0.5 for the continuity correction. This excluding zeros has a problem if there's too many of them. Particularly if you have a small sample to start with and half of them are zeros. Now your sample size is tiny, so you've lost a lot of power, but it also tends to bias the test towards the alternative. So if you have too many zeros, zeros indicate the null is true, but when you throw away the zeros, that tends to make it look more like there is a... So the test will reject the null more often than it should if there's too many zeros. The author doesn't really give any sense of how many's too many, but if you got a sample of 20 of these differences and you throw away 8 zeros, then that's starting to be quite a bit. If you throw away 2, then it's not that big a deal. Right? So if you have really discrete data, then zeros are going to be much more likely. If you're measuring, something that has decimal places, then getting exactly the same and therefore a difference of 0 is probably not going to happen very often. So, all right, we'll pick up from there next time, and we'll run one of these in SAS. So, we'll see you on Friday.